Today's topic is ionic equilibrium. So, when we deal with ionization of acids and bases, so according to Arrhenius concept, acid and bases, they are able to dissociate in aqueous solution and they produce, acid produces H3O plus ions and base produces OH negative ions in the solution. And according to Bronsted-Lowry concept, acid is proton donor and base is proton acceptor. So these are Arrhenius and Bronsted-Lowry concept. Now, if we consider acid-base dissociation equilibrium of a weak acid, weak acid give H plus ion feebly and give H3O plus and A negative. So acid gives conjugate base and water here act as a base which will gives conjugate acid. So in dissociation equilibrium, it is obviously dynamic in nature and there is a transfer of proton in forward and reverse direction. If we have strong acid, then equilibrium is going forward. Okay. If HA, that is a strong acid, then H3O plus, then HA that will donate protons and not H3O plus. And equilibrium move in the direction of formation of, always equilibrium moves in the direction of formation of weak acid and weak base. So why is it so? Because stronger acid, they donate a proton to the stronger base, because base is proton acceptor and acid is proton donor. So if it is a stronger acid, that will definitely donate a proton to the stronger base, and that's why leads to the formation of weak conjugate acid and base, because stronger acid have very weak conjugate base. For example, if we have perchloric acid HClO4, it is a very strong acid, so it will give H plus ions strongly, means it is a very good proton donor, and therefore we get ClO4 negative, which is a weak conjugate base. Why is it a very weak conjugate base? Because there is only one negative charge, and this one negative charge is delocalized on 4 oxygens. So per oxygen there is only -1/4 charge. There is a large delocalization of a negative charge, so attraction for the proton is less. Therefore it is a weak conjugate base. See, there are water soluble organic compounds like phenolphthalein, bromothiamyl blue, even methyl orange. So phenolphthalein and bromothiamyl blue, they are weak acids, and therefore they exhibit different colors in their unionized form and ionized form. Unionized form is, it is colorless, and ionized form is pink in color. So this is a useful indicator, in acid base titrations and to find out the H plus ion concentration. That's why, when we have a indicator, weak acid indicator like this phenolphthalein, let us write it as HPH. So if we add acid in it, what happened? If we have HCl, phenolphthalein is added in HCl. So, in HCl there is H plus and Cl negative ions, and there is a common ion. And due to the presence of this common ion, this is called common ion effect, equilibrium shifts in the reverse direction, and therefore phenolphthalein is colorless in acidic medium because of the more unionized form. Now, this is example of common ion effect. Now, what happened if we add strong base in it? NaOH, strong base. If we add phenolphthalein in sodium hydroxide, there is odd ion effect. Odd ion effect means this H plus ion is opposite to OH negative ion and leads to the formation of weak electrolyte, that is water, and therefore there is a removal of H plus ions, and therefore equilibrium shifts forward according to, both are due to Le Chatelier's principle. क्या बोलता है ये principle? That if product is more, then equilibrium shifts backward. If product decreases, then equilibrium shifts forward. So in this case, ionized form is more, and this ionized form is pink in color. That's why phenolphthalein is pink in color in basic medium and colorless in acidic medium. So according to Bronsted concept, acid is proton donor and base is proton acceptor. Electron pair acceptor is, according to Lewis concept, acid is electron pair acceptor and base is electron pair donor. So electron pair donor is Lewis base, electron pair acceptor is Lewis acid, and proton acceptor is base as per Bronsted-Lowry concept. And proton donor is acid. So strong base has weak conjugate acid according to Bronsted-Lowry concept, and weak base has strong conjugate acid. Now, ionization constant of water. So, autoprotolysis of water, when we do the autoprotolysis of water, that is according to Bronsted concept, if water donate H plus, so it behaves as acid, and if it accept H plus, it acts as a base. So H2O after donation of H plus becomes OH negative. So this acid has this conjugate base, and this H2O base, another water act as a base, and it accept H plus, we get hydronium ion HCO plus, and this is conjugate acid. So equilibrium constant, what is the modern symbol for hydronium ion? H plus ion के लिए what is modern symbol? It is like H plus ion is surrounded by 4 water molecules. So modern symbol for H plus ion is H9O4 positive. This is modern symbol for H plus ion. H9O4 positive. Okay, equilibrium constant. So we can write equilibrium constant as H3O plus into OH negative divided by H2O raised to power 2. Now K is equal to K into H2O, that is equal to H3O plus into OH negative, because say H3O plus means simply H plus. So one H2O is there, that's why it is K into H2O. So K into H2O is Kw, that is ionic product of water, and that is the product of proton or hydronium ion into OH negative, and value of Kw is constant at constant temperature. What is the effect of temperature on Kw? Yes, beta. What is the effect of temperature on ionic product of water? Is there any effect of? Yes, Kw increases as temperature increases because there is more ionization of water. So product of the concentration of hydronium ion and concentration of hydroxyl ion of water at a given temperature is called ionic product of water, and its units are mole square per liter square or gram ion square per liter square. Now at room temperature its value is Kw value is 10 raised to power minus 14 mole square per liter square. And you know, concentration of H plus and OH negative ion is equal because H2O give H plus and OH negative ion. So therefore number of H plus ions and number of OH negative ion, or we can say concentration of H plus and OH negative is equal, and that is equal to 10 raised power minus 7 at 298 Kelvin. We should mention the temperature. If temperature is mentioned, not mentioned, that means temperature is 298 Kelvin. So ionic product of water is 10 raised power minus 14 m square, and value of Kw is temperature dependent that we have discussed. What is the molarity of water? So it is molarity of pure water is 55.55 molar, because you know density of water is 1 gram per ml, that means it is 1000 gram per liter, and molar mass of water is 18 gram per mole, so it is 1000 by 18, that means molarity of pure water is always 55.55 molar. And ratio of the dissociated water to that of the undissociated water, that is always equal to 1.8 into 10 raised to power minus 9, because undissociated water molarity is 55.55 and dissociated water molarity is 10 raised to power minus 7, because only 10 raised to power minus 7 mole per liter of H plus ions are present in pure water, and 55.55 total moles are there per liter of water. H2O is 55.55 mole, out of which only 10 raised per minus 7 mole per liter are dissociated, and that's why the ratio of the dissociated water to that of undissociated water is always 2 into 10 raised per minus 7, or if we write in terms of percentage, it is 2 into 10 raised per minus 7%. So that means equilibrium lies mainly to the undissociated water. That's why we say that water is a very weak electrolyte. And this is known to you. Acidic means H3O plus ion are more, neutral means both are equal, basic means OH negative ions are in excess. And unit of kW, just we have discussed, it is mole per liter square. Molarity of pure water 55.55 moles per liter. Now pH. So pH is negative log of H plus ions. So it is molar concentration of H plus ion. Actually, it is not molar concentration, it is activity of H plus ions. But if solution is dilute, we take activity equal to concentration. Otherwise, pH should be equal to minus log base 10 activity of H plus ion. But for dilute solutions, activity is equal to molar concentration. Activity in detail is not in our syllabus, but question may be asked, is it activity or concentration? Then you will write that activity is the main part, but for dilute solutions, activity is equal to molar concentration. Now for at 25 degrees Celsius, pH is less than 7. For acidic solution, for basic it is greater than 7, and for neutral it is equal to 7. Okay. Now 298 Kelvin, you know Kw is equal to 10 raised per minus 14, or pKw is equal to pH plus pOH equal to 40, because pKw is minus log of Kw, pH you know it is minus log of H plus ion, and pOH is equal to minus log of OH negative ion concentration. That's it. pKa minus log of Ka, pKb minus log of Kb. So this is the question from NCERT only. The concentration of hydrogen ion in a sample of soft drink is 3.8 into 10 raised per minus 3 molar. So what is pH? So to calculate pH, we use this formula, minus log of H plus ion concentration. Obviously, hydrogen ion concentration is given to us. So minus log of 3.8 plus log of 10 raised to power minus 3, because log of A into B is log A plus log B, and log of A raised to power n is n log A. So it is minus log of 3.8 plus log of 10 raised by minus 3. So it becomes minus 3 log 10 minus plus 3 and minus log of 3.8. Now log of 3.8 is 0.58. See, log of 2 you have to keep in mind 0.3. Log of 3 is 0.477, take it as 0.48. Log of 5 is 0.699, take it as 0.7, and log 7 that is 0.84. These four logs you have to keep in mind. See, as it is log 3.8, you can, for the numerical purpose, you can take it as log of 4. 3.8 is very close to 4. So you can take it as log 4, and it is equal to log 2 raised to power 2. That means 2 log 2. That is 2 into 0.3. That is 0.6. So it is very close. It is 0.58. You can take it as 0.6. So value comes out to be 2.4. pH is 2.4. So you can guess the answer. Yes, it is very important. pH of 10 raised to power minus 8 molar. So you know, when we calculate pH by using the same formula, pH comes out to be 8. And you know, it is not true because we are adding acid into water. So pH should be less than 7. So pH of acid does not exceed 7. And therefore 10 raised to power minus 8 molar is very, we can say, diluted solution, and therefore H plus ion from water is more than H plus ion from acid. So keep in mind, if it is from 10 raised to power minus 6 to 10 raised to power minus 8, we have to add contribution from water. So that means to calculate, we have to, this is H plus ion from acid, and this is H plus ion from water. We cannot neglect H plus ion concentration from water, because H plus ion we get from acid are less than we get from water. Therefore, we add both, and therefore it becomes 1.1 into 10 raised to power minus 7. So pH comes out to be 6.958, very close to 7, but slightly less than 7. So this is the question from NEST. The exact concentration of H plus ions in an aqueous HCl solution of arbitrary concentration CHCl. Concentration of HCl is C, can be obtained from the expression. So tell me which expression is true. So see, concentration of H plus ion is equal to concentration of H plus ion from HCl plus concentration of H plus ion from water, just like this question. So say concentration of H plus ion from HCl. HCl is a strong acid. So concentration of HCl is equal to the concentration of H plus ions we get from HCl, right? Now we left with concentration of H plus ion from water. So see, if it is in terms of Kw, right? So you know what is Kw? It is concentration of H plus ion into OH negative ion. So now tell me, this H plus ion, because you know this is the container. In the container we have HCl in water. So this H plus includes H plus from HCl as well as H plus from water. But OH negative ion, you know, concentration of OH negative ion from water is equal to concentration of H plus ion from water. Am I right? Yes, beta. So that means this H plus ion concentration is not from water only. This H plus ion is concentration from HCl as well as water. So to calculate H plus ion concentration from water, it is equal to concentration of OH negative ion, and that is equal to ionic product of water upon H plus ion. So in this way, concentration of H plus ion is equal to concentration of HCl plus concentration of H plus ion from water, and that is equal to this one. That means concentration of H plus is equal to concentration of HCl plus ionic product of water upon concentration of total concentration of H plus. So this is the formula. That means B option is correct. Yes, beta, did you understand?
Yes, sir.
Okay. This is exactly the same question from in the another year. The equation appropriate for the exact calculation of pH of an aqueous solution of HCl at a concentration close to 10 raised to power minus 6. So again, you know, H plus ion concentration is equal to concentration of H plus ion from HCl plus concentration of H plus ion from water. Same question. So this is concentration of HCl, and what is concentration of H plus ion from water? It is ionic product of water upon concentration of H plus ion. That means this option is correct. Okay, ionization constant of weak acids. So when we deal with weak acids, you know, weak acids are dissociated to certain extent. So we take into account degree of dissociation, that is alpha, or we can call it as degree of ionization. Let us start with the concentration C. Initial concentration C, alpha is degree of dissociation or ionization. So after some time, means at equilibrium, C, it is C minus C alpha. So HCO plus becomes C alpha, X negative also becomes C alpha. So C is common here, C into 1 minus alpha, that is equal to C alpha, C alpha, and therefore ionization constant of acid is equal to H plus ion concentration into X negative ion concentration divided by unionized acid concentration. So in this way, Ka comes out to be C alpha square upon 1 minus alpha. But as acid is weak, so alpha is very, very less than 1. And therefore 1 minus alpha can be treated as 1 only. Therefore Ka equal to C alpha square. And alpha is equal to Ka divided by C, or H plus ion concentration is C into alpha, and therefore it is equal to under root Ka into C. So to calculate its pH, pH is equal to minus log of H plus ion, that is equal to minus log of Ka into C raised to power 1 by 2. So it is minus 1 by 2 log of Ka plus log of C. That is half minus log of Ka minus log of C. So it is equal to half pKa minus log C. So that in this way you can calculate pH. So this is the question. pH of 0.1 molar monobasic acid, it is given. So what is the concentration of H plus ion, A negative ion and HA at equilibrium, and calculate the value of Ka and pKa of the monobasic acid. So you know pH is minus log of H plus ion, and H plus ion is 10 raised to power minus pH. pH is given to you, it is 4.5. So H plus is 10 raised to power minus 4.5, and minus 4.5 can be written as minus 5 plus 0.5, that means 5 bar 0.5. That means it is 10 raised to power minus 5 into 10 raised to power 0.5. This part is positive 0.5, and this 10 raised to power 0.5, that means anti-log of 0.5 is 3.162, and therefore the value comes out to be 3.162 into 10 raised to power minus 5. So H plus concentration and A negative concentration both are equal. So H plus concentration is C into alpha. So alpha is H plus concentration divided by C. So this is degree of dissociation, and value of Ka is C into alpha square. HA is C into 1 minus alpha. pH of 0.08 molar solution of hypochlorous acid. You know hypochlorous acid is monobasic acid. It gives H plus ion. Ionization constant is given to you. So we have to calculate percentage dissociation, means alpha we have to calculate. So you know Ka equal to H3O plus ClO negative upon HOCl concentrations. So it is x square divided by 0.08 minus x, or you can take alpha here only. So it is becomes 0.08 1 minus alpha, and x is 0.08 alpha, 0.08 0.08 alpha, 0.08 alpha. So x is equal to 0.08 alpha, and alpha is equal to x divided by 0.08. So in this way, first we calculate x. That is 1.41 into 10 raised to power minus 3, and that is the H plus ion concentration. So percentage dissociation is just divided by 0.08, and we get percentage dissociation, and pH minus log of H plus. Same type of question, Ka is given to you. To calculate pH of decimolar. So decimolar means 10 raised to power minus 1 molar, means 0.1 molar. So do you know H plus is under root KAC? So we calculate H plus, and pH is minus log of H plus. So we get pH as 5. 60 ml of 0.3 molar KOH and 40 ml of 0.2 molar HCl are mixed. So what is the pH of the mixture? So see, it is acid base reaction. So obviously base is neutralized by acid. So in this way, first of all, we calculate M1V1 means number of millimoles of KOH. From next we calculate number of millimoles of HCl. So millimoles of KOH are more than KOH. Moles are more than millimoles of HCl. Therefore, it is equal to M1V1 minus M2V2 divided by total volume. So molarity, and it is base actually, which is in excess. So we get OH negative ion concentration. So OH negative ion concentration comes out to be 0.1. So from here POH equal to 1. So pH is equal to 30. So this is the question from the next exam, I think. To 5 ml of 0.1 normal HCl and 10 ml of 0.1 molar H2SO4 and 5 ml of 0.1 normal NaOH solutions, they are added together. Okay. So what is the pH of the resulting solution? So see, we have HCl and H2SO4 acids, and NaOH base. So let us calculate first number of moles of H plus ions. So number of millimoles H plus ion equal to, see, 5 into 0.1. So it is 0.5 plus 2 into 0.1 into 10. Why I multiplied by 2? Because 1 H2SO4 will give 2 H plus ions and it is molar. See, this is normal. So obviously normality is equal to molarity, and normality is equal to molarity into basicity or acidity. So what is basicity of HCl? 1. Acidity of NaOH? 1. That's why its normal is equal to molar. So in this way, but in H2SO4 it is written as molar. So it is 2 times. So in this way we have 0.10, 20, 0.2. So 0.7 millimoles of H plus ion and number of millimoles of OH negative ion, that is equal to 5 into 0.1, means 0.5 only. So what is H plus ion concentration? 0.7, because now acid is in excess. So we get H plus ion concentration. So 0.7 minus 0.5 divided by total volume. So what is total volume? 5 plus 10 plus 5, 20. That implies 0.2 over 20 means 0.1 only, or 0.01. .2 divided by 20, 0.1 divided by 10 means 0.01. .1 into 5, 0.5, 0.1 into 10, sorry, it is 2.5, right? Because it is 20 into 0.1, so it is 2.5. So in this way, H plus ion concentration is 2.5 minus 0.5 divided by 20. So it is 2 divided by 20. So in this way, it comes out to be 0.1. So what is pH? Minus log of H plus ion minus log of 10 raised per minus 1. That means pH comes out to be 1. Okay. In aqueous solution, hydronium ion gets further hydrated to give which of the following species? So that I told you that H plus ions in modern symbol, there are 4 H2O molecules surrounding H plus arranged tetrahedrally, and therefore its modern symbol is H9O4 positive. Yes, this is again question from one of the exam. Next, consider 3 vessels containing, is it visible to you? हेलो बेटा, इसको देख पा रहे हो? ये रीडेबल है बेटा? Okay. See, consider 3 vessels containing aqueous solutions of weak acid HA. Initial concentration of HA is C1. Degree of dissociation is alpha 1. HA, you know, HA gives H plus and A negative. Its concentration is given as C1. And another weak acid is HB. Its concentration is C2, H plus, B negative, and its dissociation constant is beta 2. Concentration is and their mixture HA C1, degree of dissociation alpha 1, HB concentration C2, degree of dissociation beta. Sorry, it is alpha 3. When they mix together, now degree of dissociation is alpha 3 and it is beta 3. So when C1 and C2 are varied, the correct plot, assuming alpha and beta to be small. So ये 3 प्लॉट दिए हैं. पहला है ये है, नहीं दिख रहा हो तो अल्फा 1 बाई बीटा 2 वर्सेस C1 by C2 raised to power half. In the abscissa, there is C1 by C2 only. In first case is alpha 1 beta 2. This is also alpha 1 beta 2. This is alpha 3 beta 3, alpha 3, beta 3. So these are 4 options. We A, B, C and D. We have to identify which plots are correct. So see, first of all, we have HA, which give H plus and A negative. Concentration C1, initially it is 0, 0. Now alpha 1 is degree of dissociation. So it is C1 1 minus alpha 1 equal to C1 alpha 1 C2 alpha 2. Sorry, C1 alpha 1 C1 alpha 1. So let us calculate K dissociation constant. Let us say it is Ka1. So Ka1 is equal to H plus concentration, A negative concentration divided by HA concentration. So it is C1 alpha 1 multiplied by C1 alpha 1 divided by C1 1 minus alpha 1. So C1 C1 cancel. So Ka1 is equal to C1 alpha 1 square upon 1 minus alpha 1. And you know, alpha 1 is very, very less than 1 because it is written they are very small. So therefore, Ka1 is equal to C1 alpha 1 square, or that implies alpha 1 is equal to square root of Ka1 by C1. So this is alpha 1. On the same line, when we take into account HB, same expression C2 0 0, C2 1 minus beta 2. C2 beta 2, C2 beta 2. So here on the same line, let us say its dissociation constant is Ka2. So beta 2 comes out to be Ka2 by C2. So this is from HA, this is from HB. So from these two, from 1 and 2, alpha 1 by beta 2 is equal to square root of Ka1 by C1 into C2 by Ka2. That implies alpha 1 by beta 2 is equal to Ka1 by Ka2 square root into C2 by C1 square root, or we can say C2 by C1 1 by 2. So if we plot a graph between alpha 1 by beta 2 versus C2 by C1 raised to power 1 by 2, what is the nature of the graph? Is it straight line or independent? See, take it as Y. Sorry. This is M. This part is M. And C2 by C1 as X. So it is equal to Y by MX, means it is like this with slope under root Ka1 by Ka2. So that means which graph is correct? So this is wrong. It is C2 by C1, right? It should be C2 by C1 raised to power 1 by 2. So obviously this is the right graph. So for alpha 1 beta by beta 2 versus C2 by C1 raised to power 1 by 2, this is the correct graph. Now let us say about alpha 3 beta 3. Now when we have a mixture, HA plus HB, so it gives H plus ion plus A negative ion. This is H plus ion from HA plus H plus ion from HB plus B negative, right? Now concentration is C1 and C2 initially. After at equilibrium, it's now dissolution constant is alpha 3 and its equilibrium constant is beta 3, alpha 3 and beta 3. So it is now C1 alpha 3, C1 alpha 3, it is C2 beta 3, C2 beta 3. Are you getting this point? Now it is mixture of HA and HB. We are doing the question for the mixture. Now in this mixture, what is Ka1? Ka1 is H plus ion concentration into A negative concentration divided by HA concentration. So tell me, what is the concentration of H plus ions? Yes, beta. What is the concentration of H plus ion? Hello? What is the concentration of H plus ion in this mixture? नहीं, H प्लस आयन की कॉन्सेंट्रेशन क्या होगी इस मिक्सचर में? I mean to say, H plus ion total in the mixture, C1 alpha 1 from HA and C2 beta 3 from HB, both are added up. इनको क्यों ऐड किया हमने? Because here we have to write total concentration of H plus ion, because both the acids are in the same mixture. So this is H plus ion concentration. A negative concentration is simply C1 alpha 3 divided by HA. It is C1 1 minus alpha 3. And what is KB2? Let us say for HB it is KB2. So it is H plus concentration, B negative ion concentration upon HB. Again H plus concentration is C1 alpha 3 plus C2 beta 3 into C2 beta 3 divided by C2 1 minus beta 3. So 1 minus alpha 3, 1 minus beta 3, both are taken as 1. C2, C2 cancel. So from 1 and 2, Ka1 divided by Kb2, that is equal to ये पूरा C1 अल्फा 3, C2 बीटा 3, C1 अल्फा 3, C2 बीटा 3 कैंसल. 1 minus alpha 3 is taken as 1, 1 minus beta 3, 1 minus beta 3 is also taken as 1 because they are very small. C1 C1 cancel, so it is equal to alpha 3 by beta 3. So if we plot a graph between alpha 3 by beta 3 versus C2 by C1 raised to power 1 by 2, what is the nature of the graph? It is horizontal to the equation because it is independent of C2 by C1 square root. C2 by C1 square root is not appearing in the expression. It is simply equal to Ka1 by Kb2, and these are constants for acid and base, and therefore this is Ka1 by Kb2 and it remains same whatever the ratio of the concentration may be we have. So that means कौन सा ग्राफ करेक्ट हुआ? डी. सो बी और डी ये दो ग्राफ जो हैं दे आर करेक्ट फॉर द गिवन क्वेश्चन. सो याद रखना, वेन एवर वी हैव अ मिक्सचर, इफ देर इज कॉमन आयन, सो वी शुड एड concentration of common ion. That concentration, that's why what happened, if both the acids are in the same mixture, then their dissociation decreases due to the presence of common ion. Next question. Two vessels X and Y contain aqueous solutions of a weak acid HA and its salt NaA respectively, and two equilibria are like this. So first equilibria is HA to give HA plus H2O to give H3O plus plus A negative. Another equilibria is A negative plus H2O to give HA plus OH negative. A negative plus H2O to give HA plus OH negative exist in vessels X and Y. They exist in vessels X and Y respectively, and at equilibrium concentrations of HA, H3O plus and A negative in the vessel X. This is vessel X and this is vessel Y. So in the vessel X, concentrations of HA, H3O plus and A negative is C1, C2, C3, and A negative, HA, OH negative in Y vessel it is C4, C5, C6. A negative, HA, OH negative, C4, C5, C6. Let the quantity C2, C3, C5, C6 divided by C1, C4 be taken as Q. So what is the correct relation between natural log of Q versus 1 upon T? Okay. So first of all, see, in first case, dissociation constant is, let us say K, H3O plus into A negative divided by HA. H2O liquid is not appearing in the equation. So it becomes C2 into C3 divided by C1. What about another vessel? A negative, take it as Kb. See, this acid, it is conjugate base. Ha is acid, A negative is its conjugate base. So Kb is Ha OH negative divided by A negative and is equal to C5 into C6 divided by C4. And if you remember, Ka into Kb, that is equal to Kw. Do you know it? Whenever we have dissociation constant of acid multiplied by dissociation constant of conjugate base, then their product is equal to Kw. So let us multiply Ka and Kb. So what do we get? Ka is C2 C3 by C1 multiplied by C5 C6 by C4. So it is C2 into C3 C5 C6 divided by C1 into C4. So see, C2 C3 C5 C6, C2 C3 C5 C6 divided by C1 into C4. This whole is equal to ionic product of water, that is taken as Q. This is Kw, it is taken as Q. So what is the relation between Kw and temperature? What is the relation between Kw and temperature? Direct or inverse? Yes. So that means Kw versus 1 upon T. There is inverse relation. So that's why the graph which is true is, see, there is direct relation between natural Q versus 1 upon T, natural 1 upon T independent, and it is inverse relation. So this is true. Natural log of Q versus 1 upon T, that is downward movement. And one more thing keep in mind from Clausius-Clapeyron equation, natural log of K equilibrium is equal to enthalpy of the reaction. We will see in the next part. Equilibrium constant is related to enthalpy of reaction as well. So natural log of Q is equal to minus delta H upon RT plus constant. But here it is simply working like that ionic product of water is directly proportional to temperature, so it is inversely proportional to 1 upon T. So as 1 upon T increases, Kw decreases and natural log of Kw decreases. Yes, this is the question related to the topic. See, log of base 10 K equilibrium, it is given as A minus B upon T. This is already given to you. So carboxylic acids are known to form hydrogen bonded dimers of the type given below. Equilibrium constant of the dissociation of certain dimers determined experimentally for different temperatures is given. See, so as temperature decreases, equilibrium constant also decreases. Here again temperature decreases, equilibrium constant decreases. First is benzoic acid. And other one is paratoluic acid. So obviously when methyl group is attached, tell me which one is stronger acid? Benzoic acid or paratoluic? Out of benzoic acid and paratoluic acid, which one is stronger acid? You're not audible. Sorry. It is benzoic acid because electron releasing group increase the electron density in the ring and therefore decreases the acidic strength. Electron releasing groups decreases acidic strength, and if there are electron withdrawing groups increases acidic strength. Anyhow, question is different. First question is the delta H for the dissociation of paratoluic acid dimer is approximately 9,000 calories per mole. So see, it is given the plot of log K equilibrium versus 1 upon T is linear, and the variation of K equilibrium can be expressed in the form log K equilibrium equal to A minus BT. A is 2000, B is 1700 for benzoic acid, and paratoluic acid A is 2202 calories. So value is 2202, and for B it is 2000. So we have to determine the expressions that which options are correct. Already it is given that first, second and fourth options are correct. So just now I have told you that electron releasing group decreases the acidic strength. Okay, so that means hydrogen bond strength in paratoluic acid dimer is stronger than in benzoic acid dimer. That we will see from this expressions. And delta S for the dissociation of benzoic acid dimer is negative. So when dissociation takes place, when dimer dissociates, when it dissociates from the one dimer, we get two molecules. So obviously entropy will increase because number of molecules increases when breaking of dimers takes place. At the same time, log of K equilibrium is equal to A minus B upon T. It is given A minus B into T. Actually, exact relation is log K equilibrium equal to A minus delta H by 2.303 RT. This is the relation. So from this relation, minus B upon T is equal to minus delta H upon 2.303 RT. This is called Clausius-Clapeyron equation, which relate equilibrium constant with the enthalpy of the reaction. So now from here delta H is equal to 2.303 into R into B. This is delta H. So delta H equal to, in calories is given. So what is the value of R in calories? Yes, 1.987 calorie per Kelvin per mole into B. So B for toluic acid. So B for toluic acid is 2000. So into 2000. So what is the value? Take it as 2 only. To make it easy, take 2.303 as 2.3 only. So what is the value? Yes. What is the value? 9,200 calories around, right? And value is given as 9,000, means very close to it. So that's why this option is taken as correct. That delta H for the dissociation of paratoluic acid dimer is approximately. So 9,200 approximately we can take it as 9,000. Next is for benzoic acid. What is delta H? This is delta H for toluic acid. This is enthalpy of dissociation, right? Now enthalpy of dissociation for benzoic acid is 2.303 into 2 into, instead of 2000 now it is 1700 for benzoic acid. So value comes out to be yes beta. Now what is the value? 7,820 calories. Now you know benzoic acid or toluic acid, the enthalpy of dissociation that is used to break how many hydrogen bonds? How many hydrogen bonds are broken? 2. Say in the dimer there is one hydrogen bond here and other on the other side. So there are 2 hydrogen bonds. So enthalpy of dissociation, half of the enthalpy of dissociation is bond strength of hydrogen bond, that is equal to enthalpy of dissociation of benzoic acid divided by 2. That means 7,820 divided by 2. So it is 3,910 calorie. That means 3.9 calorie, very close to 4 calories. That's why the average hydrogen bond strength for benzoic acid dimer is approximately 4 calories per mole. and this hydrogen bond strength in para-toluic acid, obviously energy required to break hydrogen bond in toluic acid is more than in toluic acid, than in benzoic acid. That's why hydrogen bond strength in para-toluic acid dimer is stronger than in benzoic acid. So this is option 1, 2 and 4 are correct. Okay, so next part we will cover tomorrow, day after tomorrow, on Thursday. Okay. So up to this you will cover up. I will share the PPT and video as well. Okay. Bye then. Have you any problem in this topic particularly? Then let me know so that I will cover in the next session. कोई ऐसा क्वेश्चन है जो मतलब कोई टॉपिक इस आयनिक इक्विलिब्रियम में? तो मुझे बता देना, ठीक है ना? ओके ओके बेटा, बाय. ठीक है दोस्तों, थैंक यू सो मच टू बी विद मी. करते हैं नेक्स्ट पार्ट. कब करेंगे? थर्सडे को एट 9 o'clock.